This talk can be considered as continuation of our discussion on capacity. In my previous discussion here and there I said we cannot produce at 100% capacity. Throughput, which is what we actually produce, is usually less than capacity. In this talk I will explain throughput. I will talk again about utilization, bottleneck, and then we talk about the difference between effective capacity and theoretical capacity, and we discuss capacity leverages, and we may expand on some other issues. Throughput is number of flow units that pass an operation, an activity, or the whole process per unit of time. For example, we may say throughput is 5 per hour. Unit of time here is 5. Throughput is 0.2 per minute. Every minute, 0.2 units of product pass this operation or this process. Throughput is 8 per day. Throughput is 100 per month. The number of flow units that pass an operation or the whole process per unit of time. What we do, we go and observe the process in a couple of random situations, and we measure the number of flow units that are processed per unit of time. For example, we go to a specific clerk in Department of Motor Vehicles in random times of the day, of course not at lunchtime, and we stay there for say 1 hour and we see how many flow units are handled by that clerk. We repeat the observation say in 10, 20 other random hours and then compute the average, and that would be throughput of that specific operation. Throughput is average flow rate. Capacity is the maximum sustainable flow rate. In periods of heavy congestion, throughput is equal to capacity. Whatever capacity you have, if there are a lot of people coming, then your capacity is fully utilized. You are working at 100% capacity. If enough people are waiting in the line, that would be your 100% capacity. In a synchronized operation, we don't produce if demand is not there. Therefore, demand is equal to throughput. What we produce is for a demand, and throughput equal to demand is less than capacity. Here I want to explain the difference between cycle time and takt time. Cycle time is related to capacity. Takt time is related to throughput or demand. Cycle time is 1 over capacity. We went through this discussion before. For example, we may say capacity is 15 flow units per hour. In that case, cycle time is 1 over 15 hour. 1 over 15 hour is 4 minutes. If I do have 3 resources like this, and if this one is bottleneck resource, when cycle time is 4, that means time of this process is 4 minutes. This is the bottleneck process. However, if I have 2 units here and they form my bottleneck, and if cycle time is still 4 minutes, then TP over there is not 4 minutes. TP over here is 8 minutes. Each 8 minutes, these 2 bottleneck resources produce 2 units. Therefore, on average, every 4 minutes, they produce 1 unit. So again, in general, cycle time is equal to 1 over capacity. If bottleneck resource is only 1, then TP of bottleneck is equal to cycle time. However, if there are C resource units in resource pool of bottleneck, then TP is equal to C times cycle time. As we saw in this example, if there are 2 resource units in resource pool bottleneck, and if cycle time is 4, TP of each of those resource units is 8. Now let's look at takt time. Takt time is taken from the German word for pace. You know, we have a tool like this in music, has an arm here and it goes this way and come back, and each movement is one pace or one step. Takt time is not defined in terms of capacity, it is defined in terms of demand and throughput. And throughput is always less than capacity. If throughput is always less than capacity, then takt time is always greater than cycle time. Suppose demand or throughput is 12 per hour. Takt time is defined as 1 over demand or 1 over throughput, and that is 1 over R. And if R is 12, therefore takt time is 1 over 12 hour, and if we define it in terms of minutes, it would be 5 minutes. Capacity is always greater than throughput. Cycle time is always less than takt time. Throughput is defined based on arrival rate. So if there is a process here and arrival rate is 12 per hour and capacity or RP is 15 per hour, throughput of the system is always equal to minimum of RA and RP. Therefore, throughput of the system is always equal to arrival rate or demand. One mistake that we usually see is people refer to takt time as an element related to capacity. Some managers say that their machine takt time is 1 over 12 hour. Takt time is not defined in terms of capacity. It is defined in terms of external demand or throughput. If RA is demand or throughput, takt time is equal to 1 over RA. If RP is capacity, cycle time is equal to 1 over RP. RP always is greater than RA. In a very risky case, it may be equal to RA. And cycle time is always less than takt time, and in a very risky case, it may be equal to the takt time. Capacity always greater than demand. Takt time always greater than cycle time. In a synchronized system, takt time is the time that each station has to send one flow unit out to the next station. Chapter 4 was on flow time. We tried to minimize time, minimize flow time. Chapter 5 is on throughput and capacity. We try to maximize throughput and maximize capacity. At the same time, like flow time chapter, In throughput chapter also, we try to minimize something. We try to minimize time. What is that time? We try to minimize cycle time and we try to minimize takt time. So we can say both throughput and flow time chapters are on time minimization. In one of them, we try to minimize flow time, in the other, minimize cycle time and takt time. Now let's solve this problem, which is mainly based on the discussion we had in capacity. We refresh our mind on a couple of terms and we learn one or two or three new terms. This is a process. We have 5 activities. We do have 1, 2, 3, 4 resources, and these are the work content, the time required for each activity at each resource. Mailroom 1 minute, data entry 5 minutes, initial processing by claims processor 6 minutes, inspection by claim supervisor 2.5 minutes, and final processing again by claim supervisor 2 minutes. These are work contents. Now if you want to compute unit load for all these 3 resources and centers, unit load is equal to work content, but for this one, unit load is summation of these 2, which is 8. So unit load of a resource unit, which we refer to it as TP, the amount of time the resource have to work to process each flow unit. This includes a share of all distracts such as maintenance, repairs, setup, and so on. We refer to it as effective unit load, not theoretical unit load. Theoretical unit load is the same as effective unit load, but it is net of maintenance time, repair, setup, and all other non-directly value-adding activities. For resources and unit load of each one in terms of minutes is given. Effective capacity, as we learned, is 1 over unit load, 1 over TP. For example, if TP for data entry clerk is 5, TP for data entry clerk is 5, RP or capacity is simply 1 over 5 per, this 5 was minute, so this one is also minute. Capacity of that resource is 1 over 5 per minute. If you want it per hour, 1 over 5 times 60, 12. If you want it per day, and if day is pure 8 hours, then per day it is 12 times 8, which is 96. 12 per hour, 1 over 5 per minute. If I have TP, RP is equal to 1 over TP. If this one is in minute, this is also per minute. If this one is in terms of hour, this one would be also in terms of hour. If I have RP, that is 12 per hour, GP is equal to 1 over RP, 1 over 12 hour, or times 60, which is equal to 5 minutes. These computations are for the case when I do have only a single resource unit. If I do have a resource pool containing C resource units, and if unit load of each one is TP, then RP capacity is not 1 over TP anymore, because 1 over TP was for the case when I had only one resource unit. when I have C resource units, then RP is equal to C divided by TP. And C is the number of resource units in the resource pool. Now let's look at this situation. These are my resources, unit load, TP, minutes per claim, 1 minute, 5 minutes, 8 minutes, 2.5 minutes. Effective capacity of the resource unit, of a single resource unit, its effective capacity is 1 over TP. 1 over 1, 1 over 5, 1 over 8, 1 over 2.5. That is 1 per minute, 0.2 per minute, 0.125 per minute, and 0.4 per minute. This is my capacity. Number of resource units in the resource pool, C, 1 in the first one, 8, 12, and 5 in the last one. Therefore, if I want to find the capacity, I multiply CP by 1 over TP. I multiply these numbers by these numbers. And this is effective capacity of the resource pool. The smallest is here. Process capacity is 1 claim per minute, because capacity of the bottleneck is 1 per minute. Bottleneck is the resource pool with the minimum effective capacity. Effective capacity of the process is equal to the effective capacity of the bottleneck. Here in this situation, we can cross-train any of these people to be able to do the job of mailroom clerk, and therefore we can lift the bottleneck from 1 per minute to something greater than 1 per minute. But now we assume we stay with our system as it is. If we produce at capacity, capacity is 1 per minute. If demand is also 1 per minute, utilization of the bottleneck is 100%. A little bit variability can lead to a large number of products waiting to be processed or people waiting to be set. Suppose capacity of a process is 1 unit per minute. So in 1 hour it can handle 60 flow units. But suppose in the first 10 minutes no flow unit shows up. At the end of the first hour you have handled 50 flow units because the first 10 minutes vanished. You had 50 minutes, and in 50 minutes you can handle 50 flow units. So 10 flow units will be in the line. So you cannot perform at 100% capacity if there is a variability. In our real life, always we see variability. Imagine a freeway where we wanted to perform at 100% capacity. 100% capacity means cars are moving bumper to bumper at a speed of 65 miles per hour. As long as speed of all cars are exactly 65 miles per hour, nothing will happen. But if the speed of one of them comes down to 64.9 per hour, there will be a big accident, and it may take several hours to clean up the freeway. And all that capacity of freeway is perishable. We cannot bring it back. Do cars pass freeway easier when utilization is equal to 1 and they are moving bumper to bumper, or they move easier when utilization is 50%? So as managers, you are not going to let utilization to go to 100% for a long time, because then you will see some unpleasant waiting lines, which may take a long time to clear it up. Therefore, because 100% capacity utilization is not possible for a long while, throughput is always less than capacity. Utilization is always less than 1. The situation gets worse if you have several resources being utilized at 100% capacity. Remember in the capacity lecture, we had some situation where both oven and human resources, both capital resources and human resources at two different operations were performing at 100% capacity. This situation is much riskier than the situation when we have only one resource pool performing at 100% capacity. And that one is risky enough too. So we really don't want to perform at 100% capacity. Throughput is always less than capacity. Takt time is always greater than cycle time. In this example, let's suppose throughput is 400 per day. Because we work 8 hours a day and we assume all those 8 hours are purely available. Availability of that 8 hours is 100%. We have no waste factor. So we can assume that 480 minutes is available. And we do have capacity of our resources. And we do have available time of each resource. These are capacities. And this is the throughput. And these are utilizations. The bottleneck resource has the highest utilization. The utilization of other resources is lower. And we can cross-train them to help the bottleneck resource. Utilization of the process is throughput divided by the effective capacity of the bottleneck resource. Now, let's look at some other metrics of this problem. We know a day is 480 minutes. Each minute we can produce one product. Therefore, in a day we can produce 480 product. That is our process capacity or RP. Cycle time, in general, we say it is 1 over RP. And therefore, cycle time is 1 over 480 days. Because in one day we produce 480 units. The time interval between exit of two consecutive products from our production system is 1 over 40 day. And that is the same 1 minute which we had. We already knew that cycle time is 1 minute. Throughput is 400 per day in this problem. R equal to 400 per day. Takt time is related to demand or throughput if demand is equal to throughput. Cycle time is related to capacity. Demand or throughput should be always less than capacity, and therefore cycle time should be always less than takt time. And that is correct because takt time is 1 over 400 day, and if you multiply it by 480 minutes per day, that would be 1.2 minutes for takt time, while the cycle time is 1 minute. Flow time, as usual, is summation of the time in different stations, and that is 16.5. So each unit of product which enters our system will be there, theoretically would be there at least 16.5 minutes. Our production system can send out one product every 1 minute, but demand and throughput is less than capacity. Therefore, instead of every 1 minute, every 1.2 minute, 1 unit of product exit the production system. Now let's look at the slight variation of this problem. Here, out of what we process, 60% is physician claims and 40% is hospital claims. Unit load for physician claims are here. Our first resource pool is loaded 1 minute per physician claim. The second resource pool is loaded 5 minutes, the third 8, and the fourth 2.5. The same as what it was before. But 40% of our claims is hospital claims. And those claims have these unit loads on different resource pools. 60%, 40%. Therefore, if you want to combine these two and look at it as an aggregate product, which is 60% physician claim and 40% hospital claim, then I should say 0.6 times 1 plus 0.4 times 1.5, and that would take me to 1.2. I can do the same for the second resource pool. I have 60% here, 40% here, 60% times 5, 40% times 6, 5.4. Again, 60% times 8, 0.6 times 8, plus 0.4 times again 8, and that is obviously 8. And that's what you see here. And finally, this one times 60% and this one times 40% and add them together, and that would give me 3.1. Now I have my unit loads, and effective capacity is simply 1 over unit load. 1 over 1.2, I will get 0.83. 1 over 5.4, I will get 0.19, and so on. In this resource pool, I have only 1 resource unit. In this one, I have 8 resource units. In this one, I have 12 resource units. In this one, I have 5 resource units. If I multiply effective capacity by the number of resource units, I will get the capacity of the resource pool per minute. Why I do get it per minute? Because these numbers, and therefore these numbers, were in minutes. So these are capacity per minute. If I multiply by 480 minutes per day, I will get capacity per day, which is here. Therefore, the capacity of this process is 400 units per day. 400 units of what? Of something which is 60% this one and 40% this one. I have melted these two into each other, and I have created this aggregate product, which I know I can produce 400 units of that per day. This 400 units is 60% physician claim, which is 60% times 400, and that is 240 per day, and 160 hospital claim. So my capability is 400 aggregate products, which is 240 physician claim and 160 hospital claim. Because throughput is exactly equal to capacity, I am working at 100% utilization, which is not very safe.